Already we have seen how to design a feed forward control. How to design a feed forward controller. In that case, whatever we have seen is physically realizable feed forward controllers. Sometimes the feed forward controllers may not be physically realizable. Such controllers we'll see today. On the day, what we got is the feed forward controller equal to G D of S, disturbance model for which we are designing for the controller upon GP of S, input output model. This is called input output model. This is disturbance model. The feed forward controller is the ratio between disturbance model and input output model. Sometimes it may be unrealizable. On the day, what we have seen is we are having 4 tanks. We had the mathematical model of each tank is 1 upon S plus 1, 1 upon S plus 1, 1 upon S plus 1. The composition control of the last tank, 4th tank, has to be controlled. For that, the reagent is added in the second tank. The first tank is not involved in that. So this is the composition control. Set point is given. Composition transmitter is used. That's all. In that case, the input output model is 1 upon S plus 1 whole cube. Disturbance is entering here. That's why the disturbance model is 1 upon S plus 1 to the power 4. So if you find the controller GF of feed forward controller equal to disturbance model upon S plus 1 to the power 4 upon 1 upon S plus 1 whole cube. This is feed forward control. That is equal to 1 upon S plus 1. This is physically realized. That we have seen. Suppose I'm having a system in which disturbance is entering here. Disturbance is at the second tank. So this is not in the loop. Here, the disturbance model is 1 upon S plus 1 whole square. And input output model is the same. Therefore, feed forward controller equal to disturbance model 1 upon S plus 1 whole square divided by 1 upon S plus 1 whole cube. That is equal to S plus 1. This is not physically realizable. We know that all practical system, the denominator polynomial must be greater than numerator polynomial. Here, the degree of denominator polynomial is 0. The degree of numerator polynomial is 1. So this is greater than this. This is not physically realizable system. That's why it is not possible to find such controller. That physical controller not available. That's why even we designed a feed forward controller that is equal to S plus 1. It cannot be implemented. We'll see such problem now. Suppose we are having a 4-tank process. The mathematical model of each tank is the time constant is 1. Each one is first order, and the gain also 1. Therefore, each is s plus 1. For convenience, we are taking like that. The reagent will be added here. The reagent will be added here. It is coming from another tank. This is controlled by a composition controller. For that, the process variable is measured in the final tank. Here, the input output, the disturbance is entering here. Disturbance is entering here. Therefore, the disturbance model is 1 upon s plus 1 whole cube. Input output model is input output is given in the fourth tank. 1 upon s plus 1 to the power 4. Therefore, the feed forward controller, as we have discussed in the previous class, gd of s upon gp of s, that is equal to 1 upon s plus 1 whole cube upon 1 upon s plus 1 to the power 4. If we simplify this, what you will get is, you will get s plus 1. This is not physically realized. Not physically realizable. So in that case, what we can do is, we can add some small time constant in the denominator deliberately. Let us include gf of s, that is feed forward controller, equal to s plus 1 as we derived. The denominator we can include a small time constant, 0.1 s plus 1, like that. Now it is become physically realizable. Now it becomes physically realizable. This type of controller is called lead lag network. Lead lag network. Now let us see the simulation. Here, the disturbance is entering at the second tank. The input output model is 1 upon s plus 1 to the power 4. Disturbance model is 1 by s plus 1 to the power 3. Therefore, the feed forward controller is minus s plus 1. That is minus s minus 1. But it is not physically realizable. That's why we are deliberately dividing by 0.1 s plus 1. So this is the controller. This is the controller. In this case, now let us compare feed forward controller and feedback controller. For that, let us remove the link for that feedback controller. Let us use only feed forward controller, and here the second simulation is only feedback controller. We are going to compare feed forward and feedback controller. For the disturbance, we are not going to give any servo response. Servo response, let us make 0. No servo, only regulate, only disturbance. So here also only disturbance is given. Only disturbance is given. The second disturbance, we make that also equal to 0. Now let us check the simulation. The disturbance is given at the 40th second. The red is feedback controller. Feedback controller also takes necessary action to control the disturbance, but after the effect is sensed by the sensor, then only it takes action. But feed-forward controller senses the disturbance, not the response. The feedback controller is based on response. Feed-forward controller is based on disturbance. You can notice that small deviation is there in the feed-forward controller. That's why feed-forward controller will be better, gives better dynamics than feedback controller. Now, let us check for other disturbances, how it works for other disturbances. The other disturbances for which it is not designed. Let us give another disturbance at the 80th second. Here we are giving at the 80th second. Here also we are giving at the 80th second. Final value is 1. So for this, what happens? Let us check. So we are giving two disturbances. One is one disturbance is at 40th second. That is given at the input for which we designed a feed-forward controller. Another is given at 80th second. For that, there is no feed-forward controller. So let us check. Here, you notice that for first disturbance, feed-forward controller is designed. That's why it effectively rejects the disturbance. It is better than feedback controller. Here, in the second disturbance, which is given at 80 second, there is no feed-forward controller for the disturbance. But feedback controller controls and bring back the process to again that nominal operating point. But in the feed-forward controller, for this we didn't design any controller. That's why it deviates the process from 0 to, that is from nominal operating point to some other operating point. It is deviated. The black is only feed-forward. So feed-forward controller will not work for other disturbances. Feedback controller works for all disturbances. That is the main difference. Now let us give servo also. Servo and with feedback, because it will not work for servo response. That's why we included one more PID controller. And we are going to give servo response also. So the final value is 1. Final value is 1. That's all. Now let us check the response. Now we gave all servo. There is no difference between the two, because only feedback controller controls the servo response, set point change. So both are one over the other. For this disturbance also, feedback controller controls the output disturbance. But for input disturbance, feed-forward controller controls. That's why the dynamics of the feed-forward controller along with feedback controller gives better dynamics. Here it is the combination of feedback and the feed-forward controller. The disturbance for which the feed-forward controller is designed gives better dynamics than feedback only. That we can see now. That is the response that we have seen. So if you see the ISC IAE, if you see, it is for 9 feedback and feed forward. If you use 9, 4.84. Here is 12 and 5. So with the feedback forward controller, it gives better dynamics that we can notice. So if the controller is not physically realizable, they can deliberately add something in the denominator so that it becomes physically realizable. So if you give instead of 0.1, if you give some other value, say 0.9, how the response is, that we will check. Why we are selecting very small value? This is a lead lag network. This is the lead lag network. Here, instead of 0.1, we put 0.9. How the response is. So here, IAC increased, but better than feedback alone. We see this with the feed forward. Now let us see both. You see that with the feed forward gives better dynamics than feedback only for the disturbance for which the feed forward controller is designed. Other responses same. So even if it is 0.9 in the denominator, it works. It gives better dynamics that we can notice. That's all about feed forward.